Hello friends, and welcome in another lecture of digital communication, wherein we are going to start today with the types of quantizers and the compounding process involved in the digital communication part. In previous lecture, we have completed the derivation related to the SNR of PCM system, where we have concluded with the equation of SNR for PCM is equal to 1.86 plus C, and we have commented finally that for every single bit increment in the PCM word, the PCM SNR value is going to increase by 6 dB. So with that conclusion, we have stopped in the last lecture. Now we are starting with the types of quantization. Quantization is the process of rounding off of the levels to the nearest predefined level for every sample value. For doing this process of rounding off, we are having two major types. One is named as uniform and other one is non-uniform. To distinguish between them, when for every part of a level quantization we are having the step size value constant, it is termed to be the uniform quantization. But if the step size value goes on changing with respect to the change in your applied input, then that process will be termed as non-uniform quantization. Further, this uniform quantization will be again distinguished as mid-rate quantizer and mid-rise quantizer. So in detail, one by one, now we are going to see these uniform, non-uniform, mid-rate and mid-rise quantizer, wherein we are starting with the mid-rate type of uniform quantizer. In this black marked waveform, we are having this staircase presentation, but please take a note that in this staircase waveform, the level portion, which is known to be the trade of the signal, the trade is going to match at the center point of this origin. And this center point of the trade, when matches with the origin, it will be said to be the mid-trade type of quantizer. And it is mid-trade uniform because the step sizes for these all step size waveform will be common with the value of S. So here you can see each of the step size variation for the level is going to be incremented on vertical axis with the value of S. While on this part also, we are finding out that the decision levels are going to change with S. In other words, we can say the difference between the two consecutive decision levels on the x-axis are going to differ with the value of F. Now we will switch towards the part of mid-rise quantizer. The change which we have to observe is again at the point of origin for this characteristic plot. In the previous case of mid-trade quantizer, the level midpoint was coinciding with the origin of the characteristic plot, while in this mid-riser type of quantizer, the rising portion midpoint is going to coincide with the origin of the characteristic plot. But the similarity what we are going to observe is that on x-axis always the decision levels, that is quantizer input, is going to be marked, while on y-axis the representation levels, that is quantizer output, are going to be marked. Those are not going to change. On the y-axis, the representation levels are marked and they are going to change with the constant difference value of S. Similarly, on the x-axis, the decision levels are also going to differ with the value of S. I have told you that the quantization noise is always going to vary from the value of minus s by 2 to plus s by 2, and that's what we are observing in this lower diagram, wherein the quantization error is going to change in between the levels of minus s by 2 to plus s by 2. Either you consider the mid-rate type of uniform quantizer or mid-rise type of uniform quantizer. But the major observations from this uniform type of quantizers that we can draw is these two quantizers are memoryless quantizer. Now what is the meaning of memoryless quantizer? Here, every time the current output is always determined with respect to the current input for that quantizer, and dependent upon the previous value or the next input of the analog sample for the quantizer block. And that's why the uniform quantizers are always named as a memoryless quantizer. Here, the overload levels, that means the decision levels, are always seen to be the half of peak to peak range of input sample values. That means here we can observe that half of the portion for the riser is going to lie below this reference level and half of its portion is going to lie above this reference level. Now we will switch towards the non-uniform quantizer. Generally, the quantizer is doing the rounding off of the values. That means if I am saying that there is 1 volt level change at the input, I am not going to exactly observe that 1 volt level has been changed in the output. That because of this, we can say that even though there is 1 volt change at the input, that will not be reflected as 1 volt change at the output. So this is a non-linear behavior of the quantizer. And whenever the non-linear behavior of the quantizer is to be seen, definitely the step sizes also should not be constant. Instead of that, the step sizes should be variable. And why those step sizes should be variable? That is because the amplitude of the input signal continuously goes on changing. Generally, in all the real-time experiments, this non-uniform type of quantizer has to be applied because in real-time signals, always the amplitude variations will not happen with the same magnitude. And so we have to follow the part of non-uniform quantization. To comment on step size increment or decrement, the nature of original signal has to be looked for. So if the step size has to be reduced with some reduction level, then we are saying that their non-uniform quantization is to be applied. Generally, for the weak signals, the step sizes are to be kept very small so that the quantization noise will reduce, but it will improve the SNR value, that is signal to noise quantization ratio. The step sizes will go on vary, and this step size variation has to be applied to change the value of quantization noise. And quantization noise value should be changed to maintain the proper SNR. And this proper maintenance of SNR is the major task of non-uniform quantization. And the best process which is depicting the non-uniform quantization is the compounding process. So what is mean by compounding? So compounding is a type of non-uniform quantization which is used to maintain the SNR value of the signal at particular level, even though your signal at the input is either taking a larger value or it is weak at the input side. Whatever may be the input signal level change, your SNR should be maintained with the constant value, and that is the task of compounding process. To understand this compounding process, we will again start with the quantization noise value that we have derived in SNR equation. So we have commented that quantization noise will be with the magnitude of S square divided by 12. In the uniform quantization, once we have defined the step size, and as the step size is remaining constant, always the quantization noise power also will remain constant. But as we have said, the real-time signal goes on changing their magnitudes continuously. The signal power value will not remain constant, and it will be proportional to the signal amplitude square, because power is nothing but amplitude square. So if the signal power is small for the weak signal, but the quantization noise power is constant, definitely the SNR value for that will become very less, or it will be very poor. And this is going to affect the signal quality when we are applying that signal for on the larger distance. So here the remedy or solution for this problem is applying the device which will maintain proper SNR, and that is the compounding block. So the compounding term is basically consists of two processes. One is compression and other one is expansion. But in the non-uniform quantization, this process's implementation is very difficult, because on the transmitter side, if any of this operation of either compression or expansion we are carrying out, the opposite operation has to be implemented on the receiver side to regain the original signal. And that's why it is said to be having difficulty in implementation of non-uniform quantization. If the weak signals are there, those are to be amplified, and the strong signals are present, then those are to be attenuated. But in practical application and implementation of the non-uniform quantizer, basically uniform quantizer itself will be used. And this block of compounding will be shown to be the input signal will be taken. On the transmitter side, compressor has to be applied for the stronger signal. Uniform quantization of compressed signal has to be carried out, and on the receiver side the expander block has to be implemented, and such how the original signal will be recovered as an output from this expander. So this is what said to be the model of compounding process. But if originally the signal is weak, then at the initial stage, instead of compressor, we have to implement the expander. Then the uniform quantization has to be applied, and on the receiver side, opposite of the expander processing, the compressor block has to be applied. Now, one by one, we are going to observe for the characteristics of the compressor and expander block. So compressor is going to provide the higher gain to the weak signals, and they are going to provide the smaller gain to the strong input signals. Thus, here by using the compressor, weak signals will be artificially boosted to improve the signal to quantization noise ratio. So here in the characteristic plot of the compressor, x-axis is marked as a compressor input and y-axis is marked as a compressor output. When the input signal level is low, its gain has to be increased. That means in the range when the input signal values are lower as compared to these input values which are larger, here the output value goes on increasing continuously. But after certain input range of compressor, here the output value has been kept constant to keep the SNR value constant even though the input value goes on increasing. This is how the compressor characteristic helps us in boosting artificially for the weaker signal. Alternatively, in the expander characteristic, what we can see is this expander is ensuring all artificially boosted signals to be compressed back to their original levels. So here suppose in this characteristic, the expander input which is low originally, then output has to get increased, and that's why here as we have seen that in compressor, when the level of the original signal is less, that time the gain has to be increased. So oppositely here, as the input for expander goes on increasing, the level of expander output has to be increased. But when it is higher, it should remain constant at certain level. So if I am going to join both compressor and expander characteristic, then we can see this as an expansion characteristic while this as a compression characteristic. Now you can find out that we have plotted these characteristic in both the quadrants of first and third. Why this is happening? Because if my compressor input is positive, definitely the expander input will be again positive. Similarly, if the compressor input is negative, the expander input also will be negative. So here in this quadrant, both the values of expander and compressor will be negative, while in this quadrant, both the values of compressor and expander will be positive. That's why in this quadrant and in this quadrant, we are going to see both the characteristics are present, because our original real-time signal is going to excurse from peak values in positive region and peak values in negative region also. Now, as already earlier we have seen that if I am applying expansion at the transmitter side, to regain the original signal, we have to apply compression on the receiver side. That means the artificial boosting has to be lowered down to get the original level of signal. This is how we are nullifying the effect applied at the transmitter at the receiver level. And so total characteristic of the compander, if we are going to observe, that will be a straight line which is passing from the origin, because here the expansion effect will be nullified by the compression effect, which will cause this linear portion characteristic to be off. Finally, we can comment that even though the compression and expansion processes are having increasing or decreasing exponential like characteristic nature, the characteristic for the compounding will be a straight line. After this, we will go through the two numericals based on the PCM process. In these numericals, what we are going to observe is the relationship between the number of quantization level, sampling rate of the signal, and the band limiting value for the signal. So in the given statement, it is said that a voice signal is band limited to 3.4 kHz. It is band limited means the maximum frequency which is going to be observed in the signal is with the value of 3.4 kHz. The system is going to follow PCM, and the rate of signaling is not going to exceed beyond 36,000 bits per second. So this is the given information for the system. Now from this particular system inputs, we have to find out the value of Fs, number of quantization levels, and the number of digits used for per word, that is the capital N. We know that sampling rate is always greater than or equal to twice of Fm as per the Nyquist criteria for getting the proper recovery of the signal. To obtain this Fs, we should have minimum of equality condition for 2 into Fs. So we have stated this Fs as Fs minimum value, which will be given as 6.8 kHz. In the numerical, it has been provided that the signaling rate should not exceed beyond the value of 36,000 bits. It should not exceed, that means the signaling rate value is less than or equal to 36,000 pi. But signaling rate small r is equal to n into Fs, where n stands for number of bits per word and Fs stands for sampling frequency. So to keep the signaling rate minimum, we will need minimum value of sampling frequency. So we have considered Fs minimum. We will put the values of Fs into this equation number 1. So our equation will become as n should be less than or equal to 36,000 divided by 6.8 into 10 raised to 3. This is how we can get n value should be less than or equal to 10.29. In this case, n value is number of bits per word. Number of bits per word should be always the integer value. So we will consider this n should be equal to 10 minimum. Again, we will consider n value that is less than 10 also will be eligible for this system implementation. So we will take n equal to 5. With the relationship of q is equal to 2 raised to n, we can find the number of quantization levels is equal to 32. Is it clear, friends? If yes, then in comment blocks, please write down clear. Let's see one another example. Read out the problem statement. So what's the given information in this problem? We have provided the input signal frequency range. We have been provided with the Fs value and the minimum SNR value for the given system. Again, it is mentioned it is a PCM system, and we have asked to calculate how many number of quantization levels are existing, how many number of binary bits per word we are going to see, the signaling rate, and the minimum transmission bandwidth that is needed. We are having data in our hand are Fs as 8 kHz and SNR value should be minimum of 30 dB. It will be applicable as greater than or equal to 30 The PCM system is having SNR equation value as 1.76, which can be rounded off as 1.8 plus 6n. The SNR, we are saying that it will be greater than or equal to 30 dB. So let's substitute this 30 dB in place of SNR. We can get the n value, which should be greater than or equal to 4.7. N is number of bits per word, which will be an integer value. So 4.7 should be rounded to the nearest value as 5. N will be assumed to be 5. So to obtain the quantization level, we are having the relationship as 2 raised to n. So this Q will turn out to be 32. To find out the signaling rate, we know the relationship. Signaling rate is equal to number of bits per word for PCM into the sampling frequency. So we will substitute the values as n equal to 5 and fs equal to 8 kilo. So signaling rate will come out as 40 kilobits per second. Now the last term is transmission bandwidth. So transmission bandwidth is always half of the signaling rate. With this relationship, we can find out the transmission bandwidth requirement with the minimum value will be of 20 kilo. Here from these two numericals, it might have understood how the required transmission bandwidth, signaling rate, sampling frequency and SNR are interrelated with each. Originally in PCM SNR equation we have commented that if a single bit in PCM word is going to increase, then its SNR is going to increase by minimum of 6 dB value. If number of bits are going to increase with the relationship of 2 raised to n, the number of quantization level are going to increase. So friends, I think you might have got cleared with the PCM system, its transmitter block diagram, receiver block diagram, derivation for the SNR, and finally the numericals associated with all these mathematical relationships that we have proved out. As a final content of this lecture, what are the advantages for the PCM system, disadvantages of the PCM system, and where this PCM system has to be applied. So to comment on the advantages of PCM system, we can see that here number of bits per word representation are less, and because of that we are having less noise which is introduced into the PCM system. So we can say that this system is having higher noise immunity. Also on the channel of the PCM system there is presence of repeaters or regenerative repeaters block, because of which signal degradation on the longer distance is going to be avoided. The PCM is nothing but the digital bits representation of the information, and that's why its storage is also possible. As the output from the PCM will be in the form of a digital bits, its coding can be done, and due to the coding, the error detection and correction is possible on the PCM transmitted signal. So these are the major advantages which are provided by the PCM system. To comment on the disadvantages, we can say we are having the encoding, decoding and non-uniform quantization process is applied into the PCM operations. The circuit will become more complex. In the quantization process, if higher bit ADC we are going to use, then the number of bits per word encoding will be go on increasing, and because of that large bandwidth requirement will be there. This PCM system will be majorly applied in the spacecraft communications and the transmission of the signal from spacecraft to the Earth stations. Also, in previous telephony switching system, the PCM was applied. We have covered with the points of companding, characteristics of companding, then characteristics of compressor, expansion, numericals based on the PCM system, advantages, disadvantages and application. Here we will stop, and in next lecture we will start with the next source coding technique, delta modulation. Until then, thank you and goodbye friends.